Okay, class. Good morning. So this is another topic in power plant engineering. So this is gas turbine. Okay. So actually, this gas turbine is utilized, of course, in a region or place or an island. Okay. So like say for example, here in our country, so in Catanduanes, Masbate, Pulilio Island, Marinduque, of course, they use the gas turbine power plant. So, because in the installation of the transmission line of the NGCP it is quite difficult. Okay, so because of the island. Okay, so here is class the basic components of the gas turbine. Okay, so basically it is composed of the compressor, the combustor, and the turbine. Okay, so the air is compressed, of course, and the compressor and it is speed to the combustor. So where the fuel, of course, and air unites in the combustor, and then to produce, of course, hot gases, and then the hot gases will lead to the gas turbine, and then the after the gases or the flue gases uh, enters the blade or strikes the blade of the turbine, then it exhausts, okay, to the atmosphere, okay. So the calculation, of course, of this topic is quite easy, okay. So another, we have here the PV diagram, okay. So take note, class, that the process here from this diagram is 1 to 2 is isentropic compression, okay? And then 2 to 3 is a constant pressure, okay, where the heat is, of course, added. And then again, from 3 to 4, so that is expansion. So again, that is isentropic. And then to complete the cycle, 4 to 1, so it is rejection of heat. And again, for T is diagram, so again, it is written here. So 1 to 2 is isentropic, that is straight line, or the line is perpendicular to the is line or the entropy line. Okay. So and then 2 to 3 is constant pressure, and then 3 to 4 is isentropic, and then 4 to 1 is again constant pressure. So take note, class, that a Brighton cycle, or yes, take note, Brayton cycle is a thermodynamic cycle utilized by a gas turbine. Okay? So a Brayton cycle is composed of two isentropics and two isobarics. Okay? So that is the composition of the cycle. Okay? So let us now proceed to the analysis of the gas turbine. So 1 to 2, again, isentropic compression, where S is equals to C. Okay? So basically, the uh, equation is PB raised to K is equals to constant, same as in the isentropic process in thermodynamics. Okay, so we're getting now the ratio of the temperature, or manipulating the equations. The ratio of the temperature is P sub 2 over P sub 1 raised to K minus 1 over K. Where, take note, class, that the ratio P sub 2 over P sub 1 is the so-called pressure ratio, or RP. Okay? So therefore, the ratio now of the temperature is equals to RP raised to K minus 1 over K. And the compressor work now is, of course, WC is equals to MCP delta T, or MCP multiplied by the temperature at the exit of the compressor minus the temperature at the entrance. Okay? So that is easy. Next, for 2 to 3, so this is at the combustor. So, constant pressure heat addition, P is equals to C. Again, for P is equals to C, Q is also equals to MCP delta T or MCP, temperature at 3 minus temperature at 2. Okay? And for 3 to 4, again, isentropic expansion. So, turbine work. Okay? MCP delta T or the MCP T sub 3 minus T sub 4 because T sub 3, we look at the TS and PV diagram, the temperature is higher at that point. Okay? So, getting now the network, of course, the network is the difference of the turbine work and the compressor work because the power utilized by the compressor is, of course, obtained from the turbine work. Okay? Okay. So, again, for W net or the work net, that is WT minus WC or work net equals to MCP. T sub 3 minus T sub 4 minus MCP, T sub 2 minus T sub 1. And of course, for the thermal efficiency, of course, that is equals to the output over the input. Okay, so what is the output? Of course, the net work equals, okay, equals to the net work divided by the heat added to the combustor. Okay, so again, so also from the expansion and isentropic expansion and isentropic compression, so the relation T sub 2 over T sub 1 is equals to T sub 3 over T sub 4 or again P sub 2 over P sub 1 equals to RP. Okay? So, the thermal efficiency now. So, uh, using the work net over QA. So, the thermal efficiency now is equals to 1 minus 1 over RP raised to K minus 1 over K. So, this is a thermal efficiency in terms only of the pressure ratio and K. Okay? So, for the maximum work, of course, of the system, T sub 2 is equals to the square root of T sub 1 over T sub 3. Take note, class, of this equation. So, if you use this equation, getting T sub 2, or using, of course, T sub 2, T sub 1, and T sub 3, you will find a work which is a maximum. Okay? Okay, class, so we have here an example. So, in a gas turbine unit, air enters the combustion chamber at 550 kilopascal to 27 or 277 degrees Celsius and 43 meter per second. The product of combustion leave the combustor at 511 kilopascal and 1004 degrees Celsius and 180 meter per second. Liquid fuel enters with a heating value of 43,000 kilojoules per kilogram. For fuel ratio of 0.0229, what is the combustor efficiency of the unit in percent? So take note, class, here that this is not only a function of the pressure and temperature. Take note, class, that the velocity of the gas is included. Okay, so 43 in 180 meter per second. So therefore, if the case is like that, of course, a there is always a consideration of the kinetic energy of the gas, of course, flowing. Okay, kinetic energy. Okay, so solution. Take note now that the heat, of course, added or to the heat, of course, in the combustor is, of course, the mass of fuel multiplied by the heating value. Okay, so substituting now the air fuel ratio, so multiplied by the heating value, that is equals to 984.7 kilojoules per kilogram of air. Okay, So the heat absorbed now, so from the fuel, so that is again heat over mass, okay? The same Cp T sub 3 minus T sub 2. So plus the kinetic energy 1 half mv square, okay? So that is now equal to 742.28, okay? 0.28 kilojoules per kilogram of air. So solving now for the combustor efficiency. So that is equals to, of course, the output, which is the 742.28 divided by the heat carried by the fuel, which is 984.7 kilojoules per kilogram of gas. So therefore, the combustor efficiency now is 75.38%. Okay? Thank you very much, class. So that's all about my presentation. So wait for another presentation for an additional example. Okay? Thank you very much, class.